Alright, so we are going to deep dive into a test how this actually works. Okay. Alright, so in the make random function, we are defining a size I, and then we are just going one less than the max. Okay, and we are adding the keys. Okay, so this function uses an OR bitwise operator and a left bit shift operator. Okay, so I don't know how that works, so we'll go bitwise operators and see. Right, and see why and see just go bitwise operators. I want the bitwise operations. Yes. Okay, so we will read some. In computer programming, a bitwise operation operates on a bit string, a bit array, or a binary numeral considered as a bit string at the level of its individual bits. It is a fast and simple action basic to the high level arithmetic operations and directly supported by the processor. Most bitwise operations are presented as two operand instructions where the result replaces one of the input operands. Okay. On simple low-cost processors, typically bitwise operations are substantially faster than division, several times faster than multiplication, and sometimes significantly faster than addition. While modern processors usually perform addition and multiplication just as fast as bitwise operations, due to their longer instruction pipeline and other architectural design choices, bitwise operations do commonly use less power because of the reduced use of resources. Okay, so bitwise operations, right? So I think I have these operations in the book, if I'm not wrong. I will in the arithmetic part, I think, go format, then C operators. Yeah, in chapter 5. Yeah, so okay, so we have these bitwise 1 XOR and left shift and right shift. Okay, so we don't have a bitwise not, right? Okay, or assign or equal. Okay, so we will go to AND. What does AND do? A bitwise AND is a binary operation that takes two equal length binary representations and performs a logical AND operation on each pair of the corresponding bits. Okay, so let me try and do that. Right, so let's see .h and see there are three, right? Okay, so let me declare to int 2, which is 0 0, okay, 0 1 1 0, and p is also 2, right? Now print, right, let's say a and a is this, so we'll go a, b, and a and b. Let's see what it shows. Okay, my bad. Okay, so we clear and we make main again. Okay, so 2 and 2 is still 2. Okay, how did that happen? Okay, so let's read. Okay, 1.1 is 1. Right. Right. So, if I want to make it 0, I should say b is 0. Right, and then whole thing will be 0. Yeah, okay. Then if I go 4, now I will have like say binary representation of 2 is 0010, and binary representation of 4 is it's 0100. So I will be left with a 0 again, if I'm not wrong. Yeah, it will be 0. Okay. So that is how let's say bitwise AND operation. Right. Then a bitwise AND is a binary operation that takes two equal length binaries in representation and performs a logical AND operation. Performs on each pair of the corresponding bits. Thus, if both bits in the corresponding position 1, the bit resulting 1 and anything is 0. The operation may be used to determine whether, for example, a bit is set to 1 or cleared or 0. For example, when given a pattern 001, to determine whether the second bit is set, we use the bitwise AND with a bit containing 1 only in the second bit. Oh, okay. Okay, because the result is non-zero, we know the second bit in the original pattern was set, bit setting. Okay, this is often called bit masking by analogy. Okay, the use of masking tapes cover mask portions. Okay, I should add that. We use this to check if a particular bit is set or not. 0, as none of the bits were bits matched. Notation of 20010, binary representation of 3 1. We can check if the second bit was set or not. 2 and 3 is 2, which is a positive number depicting the second bit was set. Yeah. Okay, so that's how this works, and this is called set, and this process is called bit masking. Okay. Masking tape covers portions that should not be altered or portions that are not of interest. In this case, the 0 value masks the bit that are not of interest. Okay. The bitwise AND may be used to clear selected bits of flags registers representing Boolean states. Okay, yeah, we can clear that. Ah. Okay, because of this property, it becomes easy to check parity of binary number by checking the values of the lowest valued bit. Decimal. So 6 is divisible by 2 and therefore even. Okay, bitwise OR. Okay, it adds. Bitwise OR is a binary operation that takes two bits patterns of equal length and performs a logical inclusive OR operation on each pair of the corresponding bit. The result in each position is 0 if both bits are 0, while otherwise the result is 1. Okay, we move on to bitwise OR operation. So we go int c equals 2, then int d equals 2, and I go printf or c d 0. Okay, we'll make main and 2, right, because okay, so let's say I take 4 and 2, then it should be, because 0, it is basically 4 representation of 4 is 0 0 1 0, sorry 0 1 0 0, and okay, can yep, can I copy a whole line? Of 2 is 0 1 0, therefore 2 or 4 is C. 4 and 2 is 6, so it's like 6, yeah. Okay. Well, let's say if I take something like a 5, right, and then I take a 3. Okay, so I will get with 5 and 3, we get the 4, we get the 2, and we get the 1. 4 to 1 is 7. 5 3 is 7. Yeah, okay, so that's how this works. Okay. The bitwise OR may be used to set 1 to the selected bit or register described. For example, the fourth bit of 0 0 may be set by performing a bitwise OR with a pattern with only the fourth bit is set. Okay, XOR, I don't really need to know. I need to go with bit shift. The bit shift, binary shift, yeah. Bit addressing. Yeah, okay. Left shift, logical shift, circular shift, C family of shift, yeah. In C, C++, the logical shift operators are for left shift and right shift. The number to shift, okay, the number of places to shift is given as the second argument to the operator. Assign like a rotate operator. C++ provides rotate L and rotate R, but one can be synthesized from shift operators. Okay, I don't need to rotate. I just need to logical shift. Okay, logical shift, zero for shift. Zeros are shifted in to replace the discarded bits. Therefore, the logical and arithmetic left shifts are exactly the same. Okay, arithmetic shift. In an arithmetic shift, the bits that are shifted out of either end are discarded. In a left arithmetic shift, zeros are shifted in on the right. In a right arithmetic shift, the sign bit in 2's complement is shifted in on the left, thus preventing the sign of the operand. Okay, for example, use an 8-bit register interpreted as two operands. Okay, so we would left shift. We do a single left shift. Okay, let me try this. Bitwise shift operator. Bitwise left shift. This operator shifts the bits okay, shifts the bits this operator shifts the bits in the binary string to the left, and the discarded bits are filled with zeros. Okay. Say int e equals 2, right? So go binary representation of 2 is 0 0 1 0. Okay. Then I go e left shift by 1, shifting the bits by 1 digit. And f say and shift equals 1 shift. Okay, I shouldn't do this. This part should come here. This should go away, and let's just copy and paste this here. Righty shift, and we run the new one. Okay. Oh, spelling mistake. Okay, right, because okay. The number of bits to be shifted, the second operand to the operator. Okay, right. Okay, so basically it shifts the bits as 16 digits and or the result with another RAM call. Then we add the key. Then we check order. Okay, how is that order checked? Okay, then we add these keys in the map, right? Okay, d1 and d2 and n minus 1, so if any should be okay. Since they are arranged in ascending order, the preceding key should always be larger, should always are they in preceding order? Always be larger, yeah, okay, should always be larger than the succeeding how do you spell succeeding, man? Succeeding, okay, it's single word. Succeeding key, okay, so it just checks for that and test it, just searches the data with key. Then we test for big number of elements, make map random create. Okay, I can check for 100, right? Element, okay, creates a map of size 100. Check, and we make add elements. Then we sort the map. I hope doesn't it sort itself? Check if the okay, test search, okay, intent I should be okay, I equals to map and by 2 and I should be less than. Okay, so we are finding the middle element and map, and we get the contents, which is the data and dot key. We found not null, then find dot data equals to if found dot data is equals to got wrong result looking for at okay, key data key, if it is not null we say, if it is null then we didn't find it, and if these two are equal then we got the wrong result. Okay, how does that work? Oh my god, what is the time? Okay, yeah, okay, so we decide, then we check test the search and order functionality. Okay, while map and equals to 0, find map content by 2 dot data should get a result, size old, delete. Okay, so we are deleting this element, didn't delete it. Then we go old -1, map and downside after delete. Check out a map. Map didn't stay ordered after delete. Okay, so we are also, in addition, we are also checking the delete functionality. Okay, pretty straightforward. Just I don't understand this part. I would have to take a look. Just so you can say bitwise shift, we'll go this operator shifts the bits in the binary string to the right, and the discarded bits are filled with 0. Right. Okay, so we can get rid of this. Alright. So we say we have this element. We get the content at this. Then we check. We assert that both these should be equal. If they are not equal, okay, we assert that this should not be null. Okay. We check if I equals map end, and I should be okay. How does it okay, this is the initialization, and then we keep on. Okay, we start at the middle of the and move our way to the end, right? Yeah, okay, that's what we do. Check if the element we have found are the same. Okay, then this is just same, storing the old size, checking the new size. Okay, and then I should go make md build sorry, yeah. Okay, so I would also have to open with sublime text. Yes. Build W, did I write build W? Yes, I did write build W, sorry, my bad. Let's go to make again and runs clear. Okay, so I got this right. So folks, we are finished with this. Okay. We feed the rad function with the current time. Okay, and that is all for today. So